Hello, everybody. Welcome to video 7.3. We're going to be talking about values of a ratio, especially as it relates to unit rates and multipliers. This is going to be a pretty short one, and a lot of what's in this video 7.3 was also included in video 7.2. So I will reference that a little bit. Well, I'll call back to that. But if you've watched 7.2 and then this video back to back, it's going to seem like there's a lot of overlap. There is. If you watched 7.2 a while ago and you're just not getting around to 7.3, you may feel like maybe you've watched this before because it does seem so familiar, and that's because it should. But there are some points that are different. It's definitely worth your time. But this will be one of the shorter ones. But either way, let's get started. So there are 2 points that I want to make from the book that are pretty important points. And the first one is that a ratio represents a pair of numbers. It is a comparison between two things. The two things might have different units. We might be talking about miles and hours, and so we'll get a rate, a speed rate out of that, miles per hour or feet per second or something like that. But a ratio can also be a comparison between two things that have the same units. And we looked at the problem before where there was cups of chicken and cups of sauce. It's all cups, but you can tell a cup of chicken from a cup of sauce. So even though the units are the same, the components themselves are very different. So in a ratio, there are two things that are being compared, and you should be able to make the distinction between what those two things are. This is as opposed to a fraction, which is a single number. Now, if I were to take a fraction, say 1/2, and I could say, well, a fraction is still a comparison. It's a comparison between one part out of two parts which make a whole. And that's true. And that fraction you can talk about as a comparison, but that fraction of 1/2 also represents a single quantity. That 1/2 is definable on its own. And those two things are very much connected. That part is a part of the parts that make the whole. So they're not as distinct as elements are in a ratio. This may seem like a really minor point, and on a certain level, it probably is. But this goes to the larger point, which is very important, that ratios and fractions are not the same thing, right? For us to not just say to classes that a ratio is a fraction or a fraction is a ratio. There are similarities, but there are probably more differences than there are similarities. Now, one thing that is a similarity is this connection between equivalent ratios and equivalent fractions. So let's say that we have, to go back to our chicken and sauce problem from before, if I have 3 cups of chicken and 2 cups of sauce, and we know that I could double that recipe and get 6 cups of chicken and 4 cups of sauce. And so I can recognize this as being mechanically the same thing as 3/2 equals 6/4, because both of these are multiplicative relationships. So I could go times 2 going from left to right, or I could go divided by 2 going from right to left. And so mechanically it's the same thing. So there is a connection that these are both, or they both can be at least, multiplicative structures, right? But again, that doesn't mean to imply that they are the same thing. They behave the same way in this case, but there are cases where they don't. Now, one example of this would be, and I'm going to erase this fractional example here. So this is a really important distinction to make. So the equivalent fractions works, but let's suppose that I have two recipes that I'm going to combine. So I have my 3 cups of chicken with my 2 cups of sauce. And I'm going to add to that 1 cup of chicken and 2 cups of sauce. So what do I get for this? Well, in this case, I would add how much chicken do I have? Well, now the total pot, I've got 3 cups and 1 cup, so that's 4 cups of chicken. And then if I add together my 2 cups of sauce and my 2 cups of sauce, I have 4 cups of sauce. Hopefully you recognize the problem here. As ratios, I can add these two things together. The amount of chicken combines, the amount of sauce combines. But if these were fractions, I would not do 3/2 plus 1/2 equals 4/4. I mean, this is greater than 1, and this is exactly 1. So you can see part of the issue here, that in a fraction, that denominator represents an idea of parts of a whole. In a ratio, it just represents one of the numbers that we're comparing. Parts of a whole don't combine when we're adding fractions like this, but the cups of sauce in this ratio do combine because I'm literally adding 2 cups of sauce to 2 cups of sauce to get 4 cups of sauce. So there are similarities, but again, there are probably more differences than there are similarities between the two. They look alike. We can write them alike. They both involve two numbers in a lot of cases, but fractions and ratios are very, very distinct. I want to look at a problem, and this is going to be very similar to a problem that we talked about in video 7.2. But I want to talk about a problem that involves unit rates. And so we're told that we can run 5 kilometers in 35 minutes. So I got two questions here. So how long would it take to run 3 kilometers? And then how far could I run in 15 minutes? And I want to, I've separated these two problems out because I want to look at these as two separate problems and see how we would solve them differently. Now, in the first case, I'm looking for how long does it take to run 3 kilometers at this current rate, right? So again, we're assuming that this rate is constant. So how long would it take us to run 3 kilometers? So the way that we talked about solving this problem in the previous video, I could do this ratio of 5 kilometers is to 35 minutes, and now I want a unit rate. And I know that I'm getting to 3 kilometers is what I'm looking for, and how many minutes does that make? So the fact that I'm looking for 3 kilometers gives me an indication of which unit rate I want to find. I want to find my unit rate of 1 kilometer. So I'm going to divide both of these by 5, and that means I can run a kilometer in 7 minutes. I might be using the word run kind of loosely, but I could go 1 kilometer in 7 minutes. And so now once I have this unit rate, I can multiply by 3, and now that's 3 kilometers in 21 minutes. Like we talked about before, some of you might be thinking, couldn't we just multiply this by 3/5? Well, of course we could. But again, this idea of working toward a unit rate, breaking this into two ideas, of first getting to 1 kilometer and then multiplying to get to the 3 kilometers, is probably going to be a little bit easier for most students to digest at first. Eventually multiplying by 3/5 might make more sense and doing it sort of in one step, but building that concept of why the 3/5. The 3 is one idea, the 5 is a separate idea. So rather than do 2 steps toward one number, I would rather do 1 step toward one number twice, and then start to fold those ideas in together. Anyway, so let's look at the second problem. How far can we go in 15 minutes? So we have the same ratio. This hasn't changed. It's still 5 kilometers to 35 minutes, right? So now I'm looking for how far I can go in 15 minutes. And so this is the reason why I wanted to look at these two problems kind of side by side, because now I'm looking for an answer that's in that's 2 minutes. And so my unit rate now is not going to be to 1 kilometer, but it's going to be to 1 minute. Some of you might recognize that the 35 and the 15 are both divisible by 5, so we could do divided by 5. But because we're talking about unit rates, I'm not going to use 5 as the unit, as strange as that sounds. I'm going to play by the rules here. But if you notice that we could do this 1 kilometer per 5 minutes. No, that's not right. Divided by 5, so we would be divided by 7. So yeah, 5/7 of a kilometer per 1 minute. Um, you certainly could do that and use that 5 minute block as sort of, but as sort of the building block for this problem. But because we're talking about unit rates, like I said, I'll play by the rules and do it to actually to 1 minute. So I'm going to divide by 35 here. And so when I divide this by 35, I get 5 over 35, which is the same as 1/7 of a kilometer. And now this should be pretty consistent. This idea here should be pretty consistent with what we got here. 1 kilometer to 7 minutes, 1 minute to 7 kilometers. I can see that from here to here that I've divided by 7, or that to go from here to here, I've multiplied by 7. So I can see that there's a connection between these, but there is this equivalency that's there, and that's obviously that's not coincidence, that's by design. So now once I have the rate to 15 or to 1 minute, I can multiply by 15, and so now I get 15/7, so 2.14 to 857 kilometers per 15 minutes. There we go. The point to this is not so much the kilometers and the minutes, but the idea of this unit rate being flexible. Am I looking for the minutes per 1 kilometer, or am I looking for the kilometers per 1 minute? And so there is a distinction between the two. If I were to do the 1 minute here on the left-hand side, if I were to do this as 1 minute, it doesn't really help me out that much because what I'm looking for is per 3 kilometers. So that's the reason why I wanted to show these two problems kind of side by side. So for your checkpoint, we have a slime recipe that combines 3/8 of a cup of glue, or a glue solution, technically, and 1/4 of a cup of borax. And so how much glue would I need for 2 cups of borax? And then how much borax would I need for 2 cups of glue? Now, how you're going to think about unit rates in this, I'll leave that to you to sort of consider how you want to construct that idea. Um, I'll give you a little bit of a hint if you're kind of having a tough time with this problem. You may want to think about common denominators. You may want to think about making these integers. Now, these are all, if, as long as these are all equivalent ratios, you can make the ratio whatever form is going to sort of make best sense for you. But I'll leave these two problems here for you to work on. As always, if you have any questions, please let me know, bring them to class, and we'll get them answered. All right, thank you.